So thank you for invitation, and I want to relate a few topics. One topic is matrix models. The other topic is something related to quantum Calogero systems, and third topic is Hurwitz numbers. But I will talk a little bit about. I don't know how to say the accents. It depends on questions I will be asked. So first let me just show what I want to present. Actually, there are two statements. One is the following. Consider some n by Gaussian complex matrix, and consider the DAG denote Hermitian conjugate complex matrix, and okay, and consider some matrix A. Then the following statement can be proven. Trace of and let us consider the elements of this matrix as bosonic operator. And there are conjugated bosonic operators, which means that commutated between Zij and Z crest J prime I prime is equal to Kronecker symbol I prime J prime. Actually, we can consider this operator, this matrix operators as a matrix of derivative.
So with a constraint?
No, it is. You see, we have bosonic operators, and we have what two types? Z and Z.
Sorry, but Z dagger is Hermitian.
Hermitian, yeah.
So I mean, this is it's not every Z which will satisfy this condition.
No, it is not a. Yes, you are right. Because I want to say there are two. Yeah. Because there are, two ways to present it. So one way is we just consider bosonic matrix-valued bosonic operators, and we do not mention that this is Hermitian conjugate operator. And the other way is present this this operator as differential operator of transposed differential operator with respect to this matrix element. You see? And yeah, let us better. We will.
That's just another way of saying constraint.
Yeah. Okay. I will not use this. No, I will. I will not use it. Okay. And this matrix will be denoted, say, as G prime. G prime. Yeah. Okay. The statement. One statement is as follows: trace of the product. This is a matrix of derivatives. Then this is a matrix. And this is some constant matrix. And we in power n. So we remember this and trace d prime z a to the power of m commutator is equal to 0. But with some, I should say that
The A is generic. There's no constraint on A.
yes, now it is.
For any
Yeah, because yeah.
So here we just apply this matrix operator to
To-
A, yes?
Yeah, but with some correction. We have dots here. Dots denote normal ordering. Normal ordering means that this differential operator doesn't act on coefficients of this very operator, but act on coefficients of this operator. Clear?
Acts on coefficients of Z.
Yeah. Mhm. I will not use that Hermitian.
Okay.
I return to it when I will speak about random matrices. So, remark that if A is identity matrix, this is then this operator rewritten in eigenvalues of Z are higher quantum Calogero Hamiltonians related to special value of coupling constant. No, people knows that eigenfunction of quantum Calogero operator are Jack functions with parameter alpha. And when this parameter alpha is equal to 1, parameter alpha, when equal to 1, it is sure function. Should I explain what is sure function, the definition?
Better to explain what is quantum Calogero model.
A quantum Calogero model is a set of commuting Hamiltonians, which looks like
You know what is classical Calogero model?
These Hamiltonians are now that small are eigenvalues of this, and d now d is derivatives with respect to this small with respect to these eigenvalues. No, what Calogero model Hamiltonian is this, and here coupling constant alpha plus Ig I'm a little bit afraid to be not exact, but like this.
So
Sorry, but like this, and this d is derivative with respect to, it is zi is eigenvalues, d zi. Yeah.
So it's just straightforward quantization of classical. You change momenta to corresponding.
Sorry. Yeah. Yes. But in quantum case, there is important coupling constant here. Actually, but I'm afraid that I didn't write it quite correctly. I forgot it.
Could you say
Exact-
minus then J below, perhaps?
No, if we write this, then
With a Z
yeah.
up there, then I would expect I would
Yeah.
expect it's ZIDI.
Okay, but then
Z should be 1 divided by ZI
No.
minus ZJ.
no, it is yes, trigonometric and okay. No, okay. But then it is not eigenvalues, but of this, but exponential of eigenvalues of these matrices.
And then it would be ZIDI probably.
Yes.
As we had at the beginning. ZIDI is actually.
Yes, in this case, yeah.
Makes sense.
Yeah, and this alpha is important. And eigenfunction of this operator is a Jack function with parameter alpha. And this, what in this case, A is identity matrix. It is the case when alpha relate to the case when alpha is equal to 1. So eigenfunction is Schur function. And there are a set of commuting Hamiltonians, they're higher Hamiltonians. For this, these are coordinates of particles. And these coordinates of particles are eigenvalues of this Z in case A is identity matrix. And in this case, it is, if it is identity matrix, then it is a well-known relation. It is relation, it is not related to the center of enveloping algebra just because these operators form enveloping algebra for Gillian. And I asked specialists in Grisha Alshansky.
The primes for the
No, no, actually, better. No, one can introduce these operators. This operator. They form. They have the same. Yeah, what this operator have the same commutation relation as matrix with yeah. And the fact with A equal with A identity matrix is somewhat some known facts, and in eigenvalues it is Laplace-Beltrami operator. Sorry, what I do not exactly remember what coefficients.
No, but this is not important.
Okay. And I asked specialists what we get if we add A. Here, don't know.
Even though this property is still true.
This property is true.
Yeah.
This I can prove it.
Yeah.
And this is the statement
How did you
which
find
is
this
proven
property? Just by chance?
absolutely from different
From some different
point of view. Yes, I considered random matrices. Then I considered some interesting equation found by Mironov, Morozov, and Natanzon, which they called generalized cut and join equation. Then I got it. It was beautiful, but I couldn't understand how they achieve it. And I achieved it by my raw means from matrix models, from a model of random complex matrices. And then, and there is some generalization of their identity, and actually their identity related to the case where A was identity matrix. And in the context of Hurwitz numbers, it was very natural to introduce here a matrix. So this way. And then I asked, is it we get commutative. And actually more general equation, more general statement. Consider so-called power sum variables. Just if we have a matrix and eigenvalues, we can construct Newton sums. And these Newton sums are called power sum variables. P1, it is just a trace of matrix. This is trace of z square and so on. And in symmetric functions, they introduce power sum variable related to a partition lambda as product. So people know what is partition. Yes, it is a set of natural number in
Сейчас, Алекс, все-таки не слышно, что...
So we introduce pk on matrix Z as sum of powers of eigenvalues. Yes, as Newton sums. And if we have a partition, yes, понятно, что такое разбиение? Partition, it's just a set of natural numbers in weakly decreasing order. So partition with parts lambda 1, lambda 2, lambda k, it is a set of numbers with property natural numbers lambda 1, lambda k.
Integers.
Integers, yes. Yeah, with this property. And people like...
The sum is partition of what? Partition of n, probably.
No, there are different...
Is it partition of n, or is it partition...
No, n will be unrelated to this. Will be unrelated.
Partition of anything?
Yes, it is partition of anything.
Okay.
I want to introduce some variable. What this variable, say, p lambda will be product of the trace z lambda 1, trace z lambda 2, and so on. The number of non-vanishing parts is called the length of partition, and some of these parts are called the weight of partition. It is, or people may be familiar with Young diagrams, it is a set of rows with number of nodes. It is lambda 1, lambda 2, and so on. Lambda 2 and so on. And this is the length of partition, length. Notation is this, and area of this figure, no number of nodes, is a weight of partition. So these are polynomials which may be treated as polynomials in eigenvalues, or alternatively, as a polynomial in entries of these matrices. Okay? And there are other set of variables called Schur functions, no, very well known. Schur functions, or the characters of the linear group, and they are related to these variables in as follows. As follows. It is no, I will not. It is actually, how to say, these are two different bases, you see? These are two different bases in the space of symmetric function. these are symmetric functions in space of eigenvalues of these matrices. But so what is lambda? Delta and lambda are partitions of the same weight. There is a related to all this symmetric group CD. D is weight of partitions, and the representation related to partition lambda. This is dimension of this representation. This is the weight of what's this D.
What is dimension and what is weight?
Let us.
Weight is the area you told us, but you didn't tell us what D is.
No, I don't want to go to representation theory,
Yeah,
but I want to. The only thing I want to say that here that there is linear dependence between two bases, and there is some with some known coefficients. This is some integer which can be explicitly written down if we know the partition lambda. I can write down it. Right? I can write down it, and this is some rational numbers known as characters of symmetric group related to representation lambda and evaluated on cycle class delta. Just for us it is better because it will be impossible. So, just some rational number. This is some integer rational number, and what's the relation between two bases. Okay.
The answer must be another, is a different Young diagram.
Yes, of the same weight. Yes. No, this but this is this character. Notice some normalized character actually. I don't want to go to the detail. It is this is this label the representation, irreducible representation of this group. Yes, and this is cycle class. So in symmetric group, each element can be presented as a product of non-intersecting cycles, and the lengths of these cycles are what these lengths of the diagram delta. So we have okay. So I mentioned Schur functions because I will use it later, but not now. I want to say that the conjecture is not actually proven in no. Conjecture is the following. Let me denote it as some letter D. D is this product that for all partitions lambda and mu, this property. It is proven quite, how to say, rigorously for Hooke partitions. Hooke partitions. Sorry, when lambda is Hooke partition and mu is any partition, and also for this partition. But I'm pretty sure that it is conjecture that it is true for arbitrary lambda and mu. And this is how to say, this is a new set of commuting differential operators, and so it is interesting. And commuting differential operators may be related to quantum operators. We have particles, and we have coordinates in quantum version to derivative with respect to position of these particles. So already this, not for arbitrary partitions, this gives some integrable system which can be called some modification of Calogero system. But modification related to alpha equal to 1. When these Jack polynomials are sure polynomials. Okay. So eigen functions for actually these operators is, how to say, it is they are not yet studied in any case, in any way, just a fact. What we have this commuting area, and then the problem is to find common eigenfunctions. This is not solved. I don't know. Okay. Now, where we, how to say, get it?
So in the case when A equals 1.
No.
In the case when A equals the identity, then you know for the first one. Do you also know for any Young diagram for A equals 1?
Yes. It is, yes.
Standard stuff.
Yeah. And this fact is known, for example, maybe found in the work of Andrei Kunkov about Capelli identities. Okay. But when it is one hook partition for any mu, this is 0. Okay? So now, how it is related to matrix models and various numbers, how to say, it is the origin of this thing. Consider a Riemann sphere. No, a sphere. We are not interested in complex structure. So just sphere, two-dimensional sphere, and we have a simplest graph on the sphere, which is it is equator, and we have a vertex on equator. Yes. It is just a result of gluing of two disks. Yeah. And we have, let us consider the sphere with 3 points. Three points. And let's consider covering of the sphere by other orientable surfaces with branch points located in here, with given ramification type. So what is going on? So if we have, so let us consider default covering, default covering, and with 3 ramification profiles given by three partitions, lambda, mu, and nu. What is I recall what is ramification profile? No, what are branch points? We have a common point, not branch point, have d preimages, but in branch point we have less number of preimages, because we have, how to say, leaves, как сказать, сливаются листы. Merge, yeah. Huh? Merge? So, вот. Merge, слияние.
Сливать.
Да. If we have local coordinates here z, it is F.
A-F-E-R-G.
Merge. Okay, merge.
Is it correct?
I think so. And here, what here it is 3 and 2. We have 3 and 2 nodes, and this is called, what this Young diagram called ramification profile in this branch point. So we have here, what are pre-images of this point? We have this called base surface. On the base, locally around this point, we have this. In case of the partition 3 and 2, we have 3 pairs of semi-edges and 2 pairs of semi-edges. This edge of graph, if we split it on 2 parts, it is called semi-edges.
Does this mean D
Semi-edges.
equals 5 in this example?
Да, D equal, yeah. Okay. So, and what is going on? What are the pre-images of this disk? It will be a set of polygons with. It will be lambda one gon. Yeah, lambda 2 gon, and so on. And it is this set of polygons is the preimage of this disk, one gon. So we have 2 one-gons and the preimages and we have some surface. No, I will say Riemann sphere, but without just orientable surface. And we have a result of gluing above it, a result of gluing of the preimages of these 2 disks. And the question, what is the number of different ways to glue this? To glue if these 3 partitions are given. So we have 3 partitions. Of course, they are of the same weight because this weight is equal to D. And let us, no, I want to, sorry. First I should say, we have 2 one-gons, and let us glue it, preimages of these one-gons in different ways. But each time we get some ramification profile in the vertex. And when we fix these 3 ramifications, we have some number. Let us denote it n. N is the lambda of n is the way to glue disks in such way that in the vertex, we have this given ramification profile. And if we denote, if we divide this number let us identify gluing of the same gons with the same number of edges. Say if lambda 1 is equal to lambda 2, we can permute them. And we say that, and also we identified the way of gluing by rotating on each gon. So we have lambda 1 rotations. So we get a number of how to say, automorphisms of this, which is equal to no, let me call it out lambda and out mu, and so if we have a partition, what for this Young diagram, this automorphism of this diagram will be 3 times 3 times 2 factorial, because and times 2. 2, we have rotate this polygon, 3 and 3 we rotate this polygon, and we can permute them. And let us call it automorphism of partition of a Young diagram. It is, some people prefer to call it, maybe it is not precise, because, okay. And this number is called Hurwitz number.
And you have to divide by out mu also.
No, because we glue polygons and we look what we get here. We get some partition, and there are, we can, you see? And this ratio is called Hurwitz number. No, it is one of the definition of Hurwitz number. And it may be shown that it does not depend on the order of these 3 Young diagrams. Okay? Now, let us turn to, we have some picture related to it. Consider some complex matrix Z, actually, right? Z and n by n complex so Z now Z will be Hermitian and A. These are G, L, and C. Okay? And let us assign to this picture the following: to the edge, to the side of edges, we associate Z and Hermitian conjugated Z. And no, let us actually let us consider two matrices A and B here. Some matrices, and A and B will be related to these corners of these one gons, A and B. And and better we relate to the entry Zij an arrow. No, say it will be, for our purpose, say let us then draw it as dotted arrow. A and J. No, just to this some arrow and 2 numbers. To that DAG, we associate this arrow. To this Z. G, E. And solid arrows to these matrices A and B. And let us consider the product of matrices what in the upper disk as product of matrix Z times solid arrow, it's matrix A. No, in this picture, the product of matrices is just arrows, how to say, the end of представленных друг другу, composition of arrows. Yes, and if we consider trace of the product of matrices, trace, it will be a chain, a closed chain. Closed chain is a polygon, topologically polygon. And this is, how to say, the reason why these operations with matrices may be related to two-dimensional physics or mathematics. Okay, we have this picture, and we have this picture. We have how to say inflate vertex, and we have the two arcs with we assign matrices A and B, and we can consider the product of ZA and the product of Z dag B. Now, now consider so-called, no, it's called Geneva ensemble, ensemble of random matrices. With it is so so it is defined on space of matrix elements of these matrices, and with the following measure, if we have some function of entries of matrix Z and Z dag, then what f is function of matrix entries. Is it clear what is written? So just Gauss integral. It means, yeah?
So we integrate along the sphere, yes?
No. So we will integrate later. Now we just would consider this. It is called, it is called in physics, it is called Geneva, complex Geneva ensemble. So we have this space of Gelian matrices, and we have a measure. And if we want to calculate an, how to say, expectation of any function of entries, we just would apply this formula. No, and some normalization constant. Normalization constant, one of the normalization constant, it is when f is unity, it is, okay? So now if we have this, one can easily check that Ij, product of Zij and Z dag Ji prime, it is di prime dj prime. We can just to understand it, let's consider n equal to 1, just complex numbers. So we consider, in this case, integrals here.
Is that with constraints or without the constraints?
No. Now, no,
Forget
no.
about that now.
There,
Okay, so
I will
this is
because
complex conjugate matrix.
yeah, because
Okay, I understood. I
yeah.
got it.
because I want. There are different ways to
Yeah.
present, and I start to mix them. So, if we have one variable, then what is the expectation of z?
One variable is the expectation of z.
Of z itself.
No, it's mod z squared you want, if you're going to do this case.
No. First, I just want to let us look here. What is it? Is 0, yes? 0. And non-zero,
Asymmetry.
yes, it is. Yes, it is non-zero if we have two numbers and z bar only when these numbers coincide. Okay. And if we have z, you see, this is a separation of all variables. So we have two. If they not coincide, it is the analog of this. Clear? Yes. If there is a difference either between I and I prime or j and j prime, yeah. So we have this, and this is how to say direct analogy with action of
Well, it's
derivative.
proportional. It's not
Huh?
obvious that it's 1, but it's proportional to this.
No, for this normalization, what for this very normalization, it is like this. If we have, but usually people in random matrices, they, no, not only, they like to add n, the size of matrices into this measure, and then it will be 1 over n. Okay, we have this, and this is how to say the origin, how we can think about this Hermitian as a derivative with respect to z. No, in certain situations. Okay. Now, so we remember it, and I okay. Now what we have, now consider the integral trace za times trace z prime z dag b with this measure. No, this measure I will denote by mu.
Are we still in the case of what dimension?
No.
Yeah, of course, yeah.
No, mu,
Yeah,
okay,
yeah.
mu is this product of all matrix elements. One can calculate it and get the answer that it is trace AB. Just calculate and obtain. And okay, and moreover, I will not. Yeah, okay, and now let us calculate this average between p lambda zA and p mu z dag b. One can, for Gauss integrals, the so-called Wick theorem is known. It is a simple thing. Perhaps people know this property of Gauss integrals that expectation values of some monomial is a product of pairwise expectation. Yeah, is it no? Wick theorem. And actually, this Wick theorem, it may be, I will say it by words, that Wick theorem, they describe all possible pairing of Z. And if we have here some No, okay. If we have here, if you remember, this is a product of traces, and we have polynomial term inside of these Gauss integrals, and the answer will be sum of all possible choice of pairings. And this is the same actually as this is the same as, how to say, черт, ну как действие, как действия производные, действия okay, yeah. If we have so we consider this expectation with the same weight of lambda and mu, then it is not vanishing. It is different if we have more z than the dag, we have 0. So it is non-vanishing, only the same weight of lambda and mu. And Wick theorem gives the number of gluing. And we get, if we divide it with these automorphisms, lambda, we get exactly Hurwitz number. No, we have, sorry, we have the following formula. We have which, how to generalize this one. You say here we have trace of AB. And here we will have AB and some partition here. But we have many opportunities to get it, and the number of opportunities is exactly Hurwitz number.
And this nu has the same weight as lambda and mu.
Да, the same,
So you're
the same weight.
a constant weight.
Yeah, weight is constant. It is, how to say, the D, this D. Okay. But very nice, it may be generalized, but I will not, perhaps, I will not.
And is there any situation when it reproduces this sure? Is there a relation between sure and
Yes.
Does
This
it sometimes relates them with which situation?
exactly.
When?
Yeah. So this formula, this formula for random matrices, it is, how to say, it is describes the ways of gluing of two disks here. No, I only mention, but will not say. There are also multi-matrix Geneva ensemble with many matrices and with many these additional constant matrices in the vertex. No, or better maybe to say in the corners of these gons. And the general problem is to glue polygons. And again, there is many ways to glue polygons. If we have given partitions for primitives of these polygons. And in the vertex, we have a set of partitions in the vertices, and we have the generalization of this formula for in this case. No, we have, no, I will not say, because it is much more refined. I should
I'm sorry,
explain.
This is all standard stuff. Is this all known, this stuff, everything?
No, this is, how to say, it is simple, but it is not
So part of this is
written down.
You discovered this.
No, it's simple.
I'm trying to follow which you discovered.
Yeah, this,
This.
But this,
Yeah.
this. And more general, for many branch points, there is analog with product of more power sum variables. Then, what if we have this formula, one can obtain formula for sure functions because they are linearly related, and because the coefficients which relate them, there are orthogonality conditions. No, it is known because these are, how to say, known. There are different, say, delta just lambda. No, there are two orthogonality conditions with respect to this, and with respect, yeah, and quite similar for when cycle structure is the same, but representations are different. And from these orthogonality conditions, we can obtain from this, we can obtain
You also have the orthogonality conditions between the p's and the p lambda.
yeah.
Something else,
Imp-
something similar.
Bit,
And the short functions also do that.
yeah. No, I can write down it, but I will not use it.
They're kind of dual.
There are two different bases. Yeah, two different bases. And from using this orthogonality by manipulations with this, we can obtain, instead of this, we can obtain actually, let me, to be quicker, we remember that we can consider this as a matrix of derivatives with respect to entries of this matrices, and we can come to the following formula. This, sorry. No, there are some steps. Perhaps I will not speak about them. With this matrix of derivatives with respect to entries, then times matrix times this matrix, then times some constant matrix S, A, and these differential operators acting on Schur function of evaluate labeled with some other partition.
Ordered again.
Huh? Normal, yes, normal ordered. Okay. Normal ordered. And this operator, this is differential operator, and when it acts on Schur function, say ZC.
The same lambda.
No, mu. Then we get the following formula. This multiplier, which is very typical in many topics. Черт, я забыл, по-моему, minus n. Забыл. Then product. Then character. Actually, not normalized character. No, better this way. Sorry, better. I'm sorry. Сейчас.
It's proportional to something.
Yeah. Z. Z AC. Like this. Sorry. Черт. Mu lambda times Schur functions, Schur functions with the same partition, but with the product, yes, A, yes, and C. But we have this formula. And when A is when A and C is equal to 1, no, identity matrices, but all this equal to 1.
Yeah.
In this case, we get cut and join, generalized cut and join equation of Mironov-Morozov-Natanson, which is a more general formula than obtained by Jackson and Goulden, and actually called by them as cut and join operator, which describe a result of слияния. Какая я снова забыл? Слияние. Слияние двух точек ветвления.
Ну, спасибо.
Нет, merge of two branch point. Yes, cut and join equation. It is cut when A equal to C equal to identity matrix. This is cut, known cut, and join equation. Generalized cut and join equation. When it is equal to unity, I saw this in formula of Natanson, Mironov, Morozov, and was how they get it. I couldn't understand. And this is a way to get it. Different way. But here there are some important remarks that in this very case, we can take lambda and mu not of the same weight. What is written here, it is when the weight of these two partitions coincide. Sorry. Yeah, it is. Yeah. And in this way, we can, there is a procedure called completed cycles, actually very developed by Kunkov and Alshansky. When we say we can consider lambda just two node partition, but we can add a leg so that the weight of this completed to cycle with the same weight of mu. And this result in some correction to this factor. Okay. And yes, and in this case, when A equal to 1, this operator is quantum Calogero with this coupling constant alpha is equal to 1, Hamiltonians. So there is a relation between quantum integrable systems and this problem of cut and join operators.
That's when A equals 1.
Yes, when A equals 1.
Calogero is A equals
Yeah,
1.
A equals, yeah, and Calogero itself when lambda is two, yeah. But
So for if you have this for A not equal to 1, it's already generalized in Calogero.
yeah, it is generalized in Calogero.
Or is it
So this was
general Hamiltonian for Calogero.
I don't know how to
Well, you can write a simple
I don't know.
example.
You see, Calogero can be written in eigenvalues and as what this, I don't know, Laplace-Beltrame equation in terms of entries. You see, in terms of entries. And here it is written in terms of entries. And it is an unsolved problem how to relate it to system of particles. But it will be, how to say, it should be looked like Calogero model with spin. Because you see, this structure should enter the answer.
I'm just curious to see what the formula looks like. For some, I don't know, in case D, for small dimension, or some concrete A.
Don't know.
Just write it
Not
down,
no.
it's got to be
Actually, I asked specialists instead of doing it. I asked specialists like Haroshkin and his pupils. They do not know because nobody considered this system. It is new integrable system. Should be. Yes, and I will not. I think, I don't know, maybe I should even finish it, because I can only formulate some more general topic, or some more general conjecture, which I checked in many cases. The conjecture about these commuting operators, but actually we need some additional structures, perhaps. We need a so-called embedded graph on Riemann surface, and we can construct multi-matrix Geneva ensemble related to this graph. It is our work. We started it with Sergei Netanzon, and then instead of considering of these two semispheres and Riemann sphere, we can consider arbitrary Riemann sphere with arbitrary but embedded graph. But graph should be so-called двудольный, как bipartite graph. And so to each bipartite embedded graph, we can relate some differential operators, which generalize the way I explained. And the conjecture is that this operator also commuting, and it was checked by hands in many cases. So if it is interesting, I can only explain how to say this construction, or maybe not. Up to you.
Yes, shortly.
Shortly, okay. So we have embedded graph. What is embedded graph? Embedded graph, that all face of this graph is homeomorphic to disk. And yeah. No, actually, it is in physics. It's called Fed graph or ribbon graph. Also, for example, we have, and for us it is interesting bipartite graphs. Bipartite, there are two types of vertices, white and black, and each edge connect vertices of different colors. And and dual, actually we're interested in graphs dual to bipartite. No, it is a little bit like a chess, how to say, шахматная доска.
Chessboard.
Yeah. Say like this, simplest on torus. These are, we have two black faces and one white faces. All of them are homeomorphic to disk. And there's one vertex. And to this picture, no, just an example, we can present differential operator. I will not, because it is long, maybe to explain. What to each edge we relate matrix and differential operator. We have actually speak about semi-edges, and one semi-edges is matrix, the other semi-edges is derivative with respect to this matrix element. And so we have as many matrices as many edges we have in this picture. And the conjecture that no, this is derivative, I say. One these operators form commuting theory. It is next generalization, because if A, even the case in case when A is equal to 1, it is not it is, how to say, it is a sort of multi-particle Calogero system, but again, I ask the question to the specialists, physics and mathematics, like Haroshkin and some other people. It is unknown. What it is this system of operator. No one considered, even in case A equal to 1. And I verified for simple Young diagrams that indeed these are commuting operators. And these operators, what of this type, they generalize cut and join operators, but they describe merge of many branch points. No, okay. Maybe that's all. Нужно было, наверное, как-то быстренько все это выписать. Что-то я не очень подготовился. Ну, просто чтобы ясно были вот результаты. Вот это вот доказано, это гипотеза. Вот. Ну, все. Спасибо за внимание. Спасибо. Есть какие-нибудь вопросы?
Сейчас мы спросим.
Угу.
Дайте
Ну,
мне, пожалуйста, вот эту, которую у вас...
Честно говоря,
Ага.
да. Что-то я не очень рассказывал подготовлено.
Questions, remarks? If you hear me, of course.
Там нет никого.
No question, no remark. In comments.
Какие-нибудь общие вопросы?
Oh, I'm afraid that nobody...
But nobody listening had a question. You see, I changed it so we can see them.
Okay, then, thanks a lot.
Да.
Алик, выключаем камеру, да? Алик, камеру выключаем.
Ну, в общем, я просто как бы понятие, такое введение вот в некую штуку. Вот.
Какой-то человек написал, что он послал вам mail с вопросом.
Ладно.
Человек Хамилтон.
Такой человек Дима Гуреевич, он очень этим интересуется, и вот для вот того случая с всеми сферами он, значит, это дело обобщает на алгебре Гетти, то есть вместо симметрических.
На какие Гетти?
Гетти, да, вместо симметрических. Кто очень хочет обобщить. Там
Я выключил или нет? Камеру.
Камеру нет. Сейчас камеру.
Нет.
Вот она же показывает.
Я вроде нажимал. Зеленая камера включает?
Нет, наверное, черная.